Now we will solve some numericals. So this is our numerical that an oil has a kinematic viscosity of 2 into 10 to the power minus 4 meters square per second and a density of 0.8 into 10 to the power 3 kg per meter cube. If we want to have a falling film of thickness 2.5 mm on a vertical wall, what should be the mass rate of flow of liquid be? So the solution is that the mass rate of flow in kg per second is W is equal to rho g delta cube into capital W upon 3 into kinematic viscosity. So we will solve this and we will get the value as 0.204 kg per meter second into capital W, that is the width of the wall. To get the mass rate of flow, one then needs to insert a value for the width of the wall W in meters. This is desired result provided that the flow is laminar and non-rippling. To determine the flow regime, we calculate the Reynolds number. Re is equal to 4 delta average velocity into rho upon mu, that is 4 into small w upon capital W into upon kinematic viscosity into density. So we will solve this and get the Reynolds number as 5.1. This Reynolds number is sufficiently low that rippling will not be pronounced, and therefore using the expression for the mass rate of flow is reasonable. So now we will solve another numerical. In this, it is asked to rework the following film problem for a position dependent viscosity mu is equal to mu naught e to the power minus alpha x upon del, which arises when the film is non-isothermal, as in the condensation of vapor of a wall. Here mu naught is the viscosity at the surface of the film and W and alpha is a constant that describes how rapidly mu decreases as x increases. Such a variation could arise in the flow of a condensate down a wall with a linear temperature gradient through the film. So we will solve this. The development follows the same steps as before up to the governing equation. Substituting Newton's law with a position dependent viscosity gives mu naught e to the power minus alpha x upon del vz dvz by dx is equal to rho g cos beta x. So we will integrate this equation and we will get the apply the no slip boundary condition at the wall allows the evaluation of the integration constant. The resulting velocity profile is vz is a function of x is equal to rho g del square cos beta upon mu naught and e to the power alpha into 1 upon alpha minus 1 upon alpha square minus e to the power alpha x upon del into x upon alpha del minus 1 upon alpha square. As the consistency check, we will evaluate the velocity distribution for the constant viscosity case, that is when alpha is equal to 0. Direct substitution leads to interdeterminate forms in the expressions inside the brackets. This issue can be resolved by expanding the exponential terms in a Taylor series. We will have these two Taylor series of e to the power alpha and e to the power alpha x upon delta, and when we substitute this expansion and simplifying, then taking the limit as alpha tends to 0, we obtain vz function of x is equal to rho g del square cos beta 2 mu naught upon 2 mu naught into 1 minus x upon delta whole square, which agrees with the constant viscosity result. From the velocity expression, the average velocity across the film thickness is obtained as vz is equal to rho g del square cos beta upon u naught bracket e to the power alpha bracket 1 upon alpha minus 2 upon alpha square plus 2 upon alpha cube minus 2 upon alpha cube. This expression also reduced correctly to the known result for constant viscosity when alpha tends to 0. So now we will solve another numerical. Air at atmospheric pressure and 200 degrees Celsius flows at 8 meters per second over a flat plate 150 cm long in the direction of flow and 70 cm wide. Estimate the rate of cooling of the plate so as to keep the surface temperature at 30 degrees Celsius. Calculate the drag force exerted on the. We have given velocity is equal to 8 meters per second, length is equal to 1.5 meter, width is equal to 0.7 meter, T infinity is equal to 200, T at surface is equal to 300 degrees Celsius, delta T is 170 degrees Celsius, film temperature TF is equal to 115 degrees Celsius. We have some properties at film temperature discussed. Density is equal to 0.9, viscosity is equal to 2.5 into 10 to the power minus 5, K is equal to 0.35 and Prandtl number is equal to 0.7. We will calculate rate of cooling. Reynolds number is equal to REL is equal to rho u L upon mu. We will calculate Reynolds number, which is 4.32 into 10 to the power 5. Average heat transfer coefficient is calculated H is equal to 0.664 K upon L into Reynolds number to the power 0.5 into Prandtl number to the power 1 by 3. We will substitute the values and calculate average heat transfer coefficient. Then we will calculate the area, and after that we will calculate heat transfer rate. Q is equal to H into A into delta T. We will calculate the value of Q, which is the rate of cooling, which is 1589 watt. Then we will calculate drag force. First we will calculate skin friction coefficient, which is 1.328 by root REL. We will calculate CF, which is 0.00202. Then we will calculate drag force. FD is equal to half into density into velocity square into area into CF. We will substitute the values and we will calculate drag force, which is coming out to be 0.05